All right. Who's here for calculus 1? Next door. Welcome. Welcome to 2026. So this is CS 7180. We're probably more seats than planned because I asked all my lab members to come and hang out with us for the day. I don't know if they're going to have stamina to stay with us the whole time, but we have a bunch of different lab members here today. So, who here is sort of not enrolled in the class, but sort of either a lab member or a collaborator or somebody who's like, hey, you should come, right? Okay, yeah, like that, right? Okay, so a lot of lab members and collaborators here. So welcome, and then everybody who's in the class. So who's in the class? Who's a PhD student? Okay. Who's in the class who's like a master's student or undergrad? Right, so it's just a couple. So this is very PhD oriented class. And then we might have a couple Northeastern postdocs mixed in here as well. So okay, so it's a new class. We're calling it neural mechanics. It's a funny field that doesn't really have a great name yet. We can call it AI interpretability. Some people call it mechanistic interpretability. I had this long email thread with Jonathan and Atticus and some other folks about what should we call our field, and so I don't know. I'm calling this class neural mechanics, but nobody calls it. But maybe that'll be a good name for a textbook. So so you can. It's okay. There's nothing wrong with. And I can also take my coat off this if you want to. This chair doesn't need to be a chair. Give somebody else. Yeah. Keep going. Sit in a little bit. All right. Welcome. All right. So who am I? Let's see. Oh, I'm David Mao. So I've been teaching here at Northeastern for 4 years now. And in my area, this is my area. So this is my research area. So you're taking a course in the stuff that I research. We're going to design the curriculum in a sort of aspirational way, where we talk about the type of research that we will do, that you will do together with me. And that'll be the exploration. So basically, the question that I've always asked in my research is, how do big neural network work? My PhD training was in studying computer vision networks, generative vision networks. How do these amazing networks know how to draw things? Which is kind of incredible. But most of the stuff that I do in my lab now is in language networks. How do generative language networks think? How do they work? How do they represent concepts? And so I think it's a super interesting time right now. So welcome to my 2026. Who here has been using AI in work? Who's been using it to do to do coding or to help them write or stuff like that? I don't know if we have. There's another chair here. You can take this chair. So I have not been using it enough. I've been studying all these generative models, but I tend to study them in very short sentences. How does a model predict the seventh word and a seventh word sentence, like this? But I've spent a little time in the last month or two trying to use AI to do work, and this is what it looks like. So each one of these things is a function in a piece of code that I was writing. And if you watch that animation from the beginning, I think we started. Watch this animation from the beginning. You can see this is like what human written code looks like. If I give this thing to play, at some point you'll see, let's use LLMs to help me out. So this is what LLM assisted code looks like. And then if you wait another few seconds, they say, why just LLM assisted? Why not use a coding agent to actually manage my repository and stuff like this. And so this is what it looks like to bring in a coding agent. You get a lot more complexity, a lot more quickly. And so this piece of code went in about a month from 700 lines of code to right now it's sitting at 18,000 lines of code. So it's like a 24-fold increase in complexity. And it's not code that I'm taking very seriously. That is a little hobby project that I sort of code while we get things like this, right? And so, so this is, yeah. So this is sort of the world that we're in, that we're living in. So I don't know how many of you like can sympathize with this experience. Like how many had this experience, right? Yeah, right. It's a little crazy, right? And so I think that there's some, and I think that all of you in this room are the early adopters. I think the rest of the world is on the brink of witnessing some of these things and trying to figure out how to grapple with these things. And so, yeah, so what the heck? So this is a very interesting time. Here we go. So I'm going to recap for folks who weren't in NeurIPS, a little talk I gave. It's just a 5-minute anecdote for a similar historical moment that appeared a few centuries ago. So this is a woodblock of the island of Murano near Venice. So Murano was a center, it's still a center of glassmaking. And they were going through a very similar historical moment in 1600, at the dawn of the 17th century. And so you can see this is actually a picture of the leader of Venice coming to visit the island of Murano, and they're depicting here with all this artistic glass and these glass works going on. So Murano was a center of glassmaking since Roman times. And they had mastered the art of making transparent glass. Nobody could make transparent glass like the Muranos. And this was traditionally used for art. It was just this intellectual curiosity. If you were really wealthy, you could buy art. It was made out of this very transparent glass. But by the time you got to to 1600, it had become very pragmatic. We had pragmatic glassmaking because they discovered that you could grind glass into lenses, and if the glass was high quality and you made lenses out of them, you could put them in front of people's eyes and cure blindness. And this doubled the productive capacity of people who just naturally lost their vision. They couldn't see, they couldn't read after they got to a certain age. And it's just this amazingly powerful invention. And I feel like, oh, it's like a similar thing to what we're living through today, right? We have these things that have been academic curiosities for a while, and we're living through this pragmatic era where we're about to unleash it on the world, right? And so, I think that's interesting. Okay, so, and I think that interpretability has a role here, and there's some similar things here. So my lab and some of the stuff we're talking about here is going to be how to crack open AI and look into it. And I think that there's really 3 perspectives on why do this. Why like look into an AI to try to explain what it's thinking inside. And one perspective is adversarial view. Talk about one's the empowerment view and one's the scientific view. And so the adversarial view is really motivated by this. It's motivated by the fact that as these AIs are getting really good, there can be a gap between what they say and what they think. And that gap can sometimes be really problematic, right? Like they might say, well, everybody's had this experience where the AI is like, my God, that is a genius idea. You are so smart. That's great. You know what I mean? And actually, I don't think the AI is thinking that really, at least not all the way through, right? Because if I go to the AI and can say, that's not really helpful to me, I'd like you to critique a little bit more. Oh man, it's brutal. It can tell me how dumb I am, right? And so there can be this gap between what AI says, what it thinks, and this gap can be quite large. It can be very important in certain situations. And if it's adversarial, if the AI is trying to lie to you, then it's very hard to figure out how to get out of this puzzle unless we figure out like how to make a lie detector. Like, can we like go into the AI's brain and figure out what it really thinks? And so this is one of the motivations. This is probably the most pragmatic aspect of interpretability, is to make kind of lie detectors or, mind readers, right? And that maybe motivates some of the projects that you guys will look at. And so, but there's a second one that I really like. There's a second reason to do this, which is the empowerment view, which is like, after we make all these AIs and we deploy them all into the world, what does that mean for us humans? After we have all these AIs that are so good at thinking, are humans not going to think anymore? What's our job? What's our role? Isn't that weird? Or another way of asking this question is, so, these AIs are being all deployed. You guys are all young people. At some point, some of you may end up having kids and they'll grow up and they'll get to middle school and they'll have grown up in an era where it's all AI in school all the way through. And will you look at your kids and think, my God, how did they get so dumb? Are people going to think anymore? Right? What's the role of a human? And so there's a second reason that it's interesting to look inside these systems, because it's a different type of activity than just taking their output. Looking inside them is taking the scientist's role, is like asking the question, what do they know inside? How do they work inside? It's a different kind of activity. And one of the ways I like looking at this is you can ask this question. There's this overlap between what humans know and what AI knows. And you can think of interpretability as trying to expand the circle of what humans know to encompass more of the circle of what AIs know. And so if an AI has some genius insight, wouldn't it be nice to be able to understand what that insight is by understanding how the AI brain is working inside, right? And so I really like this other aspect of interpretability. I think it's one of the most important things that we should be working on. I don't think that we're doing enough of it. And so if you encounter things like this, as like research things, I think that's a very ambitious direction, very interesting. And so at the bottom of the slide deck, the slide deck is going to be in the course notes on the website. You can get the readings. I've linked a bunch of the readings into the websites that you can get. There's a third reason to look into this, right? Which is that we are living in a Copernican moment. Why are we living in a Copernican moment? We're living in this Copernican moment because, up to now, whenever people have asked, what does it mean to think? The answer is always put the human mind at the center of the rational universe, because humans are our only example of a thinking being, right? And it's sort of like when, before Copernicus, people say, well, what does it mean for things to go around in space? Well, they say, well, the Earth is definitely at the center, because that's the only frame of reference that people had. And so when Copernicus says, well, I don't know, I think maybe something else should be at the center, people thought, oh, it's madness, right? So why did I mention the Venetian glass making people? Well, okay, so the Venetian glassmakers, they would understand what we were going through. So right after 1600 and 1608, some of the opticians who were grinding these glasses, they discovered this interesting thing. If you took a few lenses and you lined them up, then you could make a device that does better than glasses. It lets you see further. It magnifies. And this had amazing commercial applications, because this was the era of a lot of naval activity, a lot of trade, and people would make these spy glasses and they would use them to spot faraway ships for military purposes, for trade purposes. And so as soon as the opticians discovered that you could do this, this immediately became very pragmatic, very practical. There were spy glasses everywhere. It was an instant hit. And this secret formula for how to use glasses in this way spread through Europe like wildfire. And so the crazy thing that happened was 1 year later, this crazy guy, Galileo, in Venice, he heard about this and he says, oh, let me go to Murano and get me some lenses and make myself a telescope. And instead of pointing it at the ships, right, he pointed it at the sky, just out of curiosity. Because, he'd heard of this Copernicus guy, whatever, but nobody believed Copernicus, right? But he like wanted to see what was going on up there with the planets. And he would have never expected, when he looked at the moon, to see these craters so clearly. And he would have definitely never expected to look at Jupiter and see that the planet of Jupiter has its own moons, and that he could observe the orbit of the moons of Jupiter going around day by day. It was the first time there was really direct evidence that Copernicus was right, not just as a mathematical accident, but as a way of really describing the reality of what a planet is, that Earth is just another planet. And more so, like what a planet really is. Planets can have moons going around them. Our moon is a moon. Jupiter has moons, right? We are kind of a moon of the sun. And so why is that similar to today? Why are we in a Copernican moment? Because when we ask what is thinking, we used to only have this one reference. And clearly now we have several examples of cognitive systems that can do thinking or thinking like things. I don't know if you want to say the Earth is kind of planet-like, right? But I think they think. And this means that for the first time, instead of having to have this difficult problem of understanding thinking by looking at ourselves, we can understand thinking by looking at these devices, at these things. And when we look at these devices, we have this amazing luxury, because they're computing systems, of looking at every single calculation, every single neuron, every single moment of learning. And so it leads to this curiosity of asking again this 5,000-year-old question of what is thinking. Because, Aristotle answered this question. What is thinking means to be a rational man. Monkeys don't think. Mankind thinks. And that was the answer, right? Descartes answered it, right? I think, therefore I am, tying thinking to personhood. Like the answer has always been the same. To think is to be human, right? But actually, they were all wrong, it turns out. To think is not to be human. To think is something else. And we can study what that is now for the first time. And we can ask questions like, what is belief? What is meaning? What is agency? Maybe there's consciousness. Right? These used to be non-scientific questions, but we're living in an era where we have the chance and maybe making these questions scientific for the first time in history. So I don't know if this is the third reason. I don't know if this is not the pragmatic reason. This is not going to cure blindness, right? It's not going to solve a new military application by letting you see the enemy on the horizon, right? Which is what the other things are about. But when you point your telescope to the stars, you may end up changing the way everybody thinks about the world. And how can you resist as a scientist? So I think there are these three reasons to look at what we're doing. So welcome to 2026. We're living at this unique moment in history. Let's go on this journey together. What is this course? So it's neuroconcept research to meet a Copernican moment is what it is. And so you're all going to come along and do research with us. And we're going to do our best at trying to guide you through how to do research in this domain, equip you with the tools, and give you some space and some time and some structure to try to put together a research project. And so this is the mission that we will set in front of you if you choose to accept it. Mission Impossible. Your mission is to write a research paper or a draft of a research paper on a neural concept, like how the LLM thinks about something, some interdisciplinary concept. And so this is chosen there's a couple words here that are just a couple assumptions that I've put in here. We're going to study LLMs, language models, partly because they're so versatile and there are so many different types of concepts that are represented inside them that I don't think that it'll be too restrictive to limit to them. Of course, there's other types of systems other than LLMs to study, but there's an advantage to studying LLMs altogether because then we can all learn from each other because we're looking at the same types of systems. We can develop the same type of common language. And so there are things that are very similar to LLMs, and we probably won't study them. People will study things like protein language models, things like that. But even that is just a little bit different. And so my suggestion is let's just go and we'll study things that communicate in human language. And autoregressive LLMs even. That's it. From a technical point of view, that's pretty narrow, but from a practical point of view, that's very broad. But then let's study interdisciplinary concepts because there's been so many papers already written by computer scientists looking at these LLMs about computer science things. Like, oh my God, how many papers am I going to read about how they count? Oh, my LLM represents numbers. Count to 5. Oh, my LLM can count to 50. Right? And then here's how it does it inside another paper. Right? Well, because computer scientists don't have that much imagination. Right? And so let's like study some other things because these LLMs can represent so many different things. And so I'm intentionally trying to mix interdisciplinary researchers here in this group, and we're going to make teams around other types of things to study. So the opportunity I talked about. So we're going to structure the structured part of the class in terms of teams. So we'll probably each research team will have about 4 people, and we've pre-seeded teams, and then I know we have a lot of visitors here. So if people are willing or interested in mentoring a team as a technical advisor, then we could have mentorship as well. But there'll be like 4 people are being graded as they enrolled in the class. That makes sense? And then the tools. So I'm going to show you. So we're going to try to cover something like 10 experimental methods as the lecture content of the class or the reading content of the class. And I'll try to prepare, little experimental samples and papers for you to read, and we'll talk about these things. So the structure of the class will be, we'll learn something every Tuesday, like how some new experimental method works, and we'll talk about pros and cons and what people have done, and we'll give it a try some code and stuff. And then you guys will get your vibe coders out, and you code up some amazing thing, and then try it out, and then talk about it on Thursday, what you found. That makes sense? And apply it to your experiment, to your thing. So Tuesday, Thursday, Tuesday, Thursday. So Tuesday will be more traditional, like class. We'll talk about a reading or something like that. And then Thursday will be like little mini project updates, project presentations. If we have 5 teams, then every team will talk for a few minutes about what they're doing, maybe just even 5 or 10 minutes. And then we might have an open-ended discussion on ideas going forward. So that's the structure that I'm envisioning for the class. So there's a website. Oh, I didn't put the URL of the website, but it's called neural-mechanics.biolab.info. I can put that up here if that's helpful. So schedule. So this is on neural mechanics lab.info. Okay. Oh boy. I don't know. Not well planned. God can save us. And so you can see basically what the schedule is there for like the sequence that I'm thinking through. There's readings. And so basically with the project updates, there's going to be, we have some pace of like what we're going to try to have the project teams get to a certain point in the research. Up to a certain point, we'll adjust this based on how everybody's doing. And then every Tuesday, there's a few papers to read. I just want you to, so we're going to discuss these papers, and so there'll be a little bit of homework. It's just like 1 point per paper, which is, or actually 1 point per week, which is to submit a question about the paper. So you read the paper over the weekend, then Monday night before 10 p.m., submit in a Google form some question that you want to discuss about the paper in the class the next day. 10 p.m. so I can go to sleep. But yeah, just some question. And so it could be a question that puzzled you, or it could be a question that you want to debate because you want to discuss it. You didn't believe the author or something, and or whatever else you want to discuss. But some, so read the papers in enough detail that you can ask a question, and then we'll have these discussions in class, and then we'll do and then on Thursday we have most of the Thursdays are like what I call the thought-a-thons. So you have been doing experiments with your group over the week, and probably things didn't work, or you had to change something or whatever. Make a picture of what it is that you found, share with people how something didn't work, or whatever. That makes sense. Okay. So grading is like this. So basically, it's all about the project. So 25% is the project, 25%. We'll have these project milestones where sometimes hand in a draft or something like that. So we'll keep you on pace for actually doing that stuff. There'll be some peer reviews near the end of the class where, you give people feedback, so you get some credit for helping on peer reviews. And then 25% is like class participation. Submit a question, come to class and discuss it. Right? Make sense? That's sort of the way it's mostly a project. And it's not going to be, it's not intended to be a killer class, but I'm trying to put a little structure in it so that you have motivation to keep going. And okay, so today we're going to talk about why study neuromechanics. So I talked about the Venetian glassmakers. Okay, you got it, right? And then course syllabus. So we just did that. Dropping it now into the document at the top of the Google Drive thing. So you see that URL, what's called NDIF. It just takes a second to fill out the form to get the key requested. And similar, another thing that takes a few hours to get approval for is the Hugging Face thing. So you can get a Hugging Face account if you don't already have one instantly. It's free, but then you have to ask for permission to use Meta's models, Llama 3.1, Llama 3.2, Llama 3.3. There's separate requests you have to make for each of them. So if you can't find it, then ask one of your teammates, or you can ask me on Tuesday where to find this URL, or I'll look for URLs to stick in here. But you need to fill out a form to say, I don't know what you're agreeing to. You have to agree to something. Say, you're not going to slander Facebook or something like that. You're not going to go do something bad to Mark Zuckerberg, and then you can get permission to do research on these things. Make sense? And so, but there's 3 separate permission forms to fill out. So it's annoying if you miss one of them and then you can't study one of the llamas. Okay, so that's stuff to do. Welcome. That's your first homework over, even before the first class is over. What an accomplishment! So the upcoming homework, the things are going to be, so like next Tuesday, you'll see on the class website there's a few papers. So don't kill yourself over reading, but like read the papers. Take a look at what they're about up to the point where you can ask a question about a conversation. And submit the papers by Monday. I'll have Nikhil send out a Google form to folks and figure out something with distributing that. I'll get it. And then for next Thursday, so the teams have homework that's due 7 days from now. You guys are all gonna do your 5-minute pitch to everybody else. So each team will get up here and say, here's what we're gonna do. Here's what's gonna win our Nobel Prize. Right, here's our thing that we're gonna work on. And then so behind it will be like a 1-page development of the idea of like, here's like what we think we're gonna study and why and what makes it interesting. Here's the background, a couple points to background literature, or a couple points to what we're thinking. But then you'll have a 5-minute pitch. So work together as a team sometime in the next 7 days to put something together. It's a 7-day thing. It's not your final project. It's just a cut to get you guys thinking about what were you looking for, and to give us some structure. Okay. So, but you already have homework. So here you are. Okay, so that's that. Okay, so now, so you guys feel free to like take your seats, and we'll chat about a couple more things in the remaining amount of time. How much time do we have for this lecture? 45 minutes. Yeah, so we can talk about a few more things for 45 minutes. Uh, yeah. Yeah.
So
Yeah.
don't be like
You guys, if you guys feel like you need to communicate more information, you can also just put it directly into the Google Doc. So if you're like, oh, everybody should like make sure that your email addresses or whatever way you want to get contacted, you know, by bat phone or whatever, put that into the Google Doc. Okay.
Well, this is the last lecture of the course because the next two meetings, nominally I'll be at Los Alamos giving a talk at a symposium there. This talk is you and your research. I've given it many times. It might as well be called you and your engineering career or even you and your career. And the discussions afterwards, you know, what on earth to do? I said, good enough for Shen, good enough for Hemming. I ain't scared of nothing. Let's go ahead and see what happens. And sometimes, by copying his style, I came through to success. I deliberately copied this and that, and they fit.
So anybody ever use Hemming codes or studied, you know, Shannon entropy or stuff like there's this community of information theory folks in the early days of the development of information theory, and Hemming was one of them. Won a bunch of prizes, did a lot of foundational work, and so you know Hemming near the end of his career was recounting his experiences as a senior researcher and had a whole bunch of advice for junior computer science students of how he thought you should succeed and do research and how you should choose a research problem. And so I thought, okay, well, I've just given you some homework for, you know, picking a proposal for what your research problem is going to be for the semester. So I thought I should probably share with you my opinion of. So I have a different opinion than Hemming, but I do think he has something to say. And so if you ever like feeling like you're lacking some inspiration or something, I'm going to give you 3 resources to think about that can give you a little bit of structure for thinking about how to pick a research problem. And so the first one is to watch that Hemming video if you haven't seen it, right? It's to find it on YouTube. It's this old guy's his perspective. It might be a little old-fashioned and stuff, but still, I think that you know it's not bad. And Hemming's perspective, something like this. Hemming's perspective is you have to have courage. You have to have courage. He says there are interesting problems in the world, and most of them are impossible. And so people are afraid to look at them and to really think that they're the one to take on this impossible problem. And Hemming is like, no, you need to have courage. You need to feel like this is why you're an academic. It's because you're going after the interesting questions. So don't rule yourself out of this circle. Now, he also talks about, you know, we all live under constraints. And he talks about how, if you watch the whole video, how it can actually be really bad to have no constraints. He says, oh, it's terrible if you go to the Institute of Advanced Study and they give you millions of dollars and, you know, all sorts of life luxury, and like everybody stops being productive. And so he contradicts himself a little bit. And he says, oh, actually, there's this other thing, which is there's all these things in the world that make you timid, right? Because like you're only capable of doing certain things. You live under these constraints. You'll have certain skills, certain resources, right? Certain time, certain colleagues, whatever, right? And that means that certain questions, a very small subset, are answerable. And so I think so. The way I read the Hemming video is like, oh, good research questions. It's this art of understanding this slim intersection between all that stuff, which is the most interesting, in this stuff that's the most possible, and which seems like really simple, but you know, I think that this message is a lot of people get scared of this, and then they all work over here somewhere else in the green circle, like not at this intersection. And so like have courage, move over here. work, try to identify that slim intersection, work over here, right? And then if you already a Nobel Prize winner, then you might be over here or something like that. No, you're better off in this intersection also. That make sense? Yeah. Okay, so yeah, interesting to others, possible for you. Now, there's this other writer who wrote this really interesting thing, and here's the way I visualize his he's another computer scientist. His name is Nielsen, and so I also linked to his essay about what makes good research. And the way I think of it is this: is that you have certain skills, right? And there's stuff that you know really well, and there's stuff that's just at the edge of like possibility where you can just barely do it, like in these little corners, right? And everybody has there's like this is like the realm of possibility. The realm of possibility is not uniform, right? There's stuff that everybody can do, and then there's stuff that like very few people do, but maybe you're a weirdo and you can do this. Like maybe you can juggle in a funny way that nobody else can, right? And that's just way out here. You can play some instrument, right? And so that's kind of interesting. And then the set of things that are interesting to do as research also is like that. There's also stuff that's just interesting to everybody. Everybody thinks it's obviously interesting. Like it's just clearly interesting. But then there's also stuff where you have a weird interest in this, right? Like you can see that it's interesting, but most people don't think it's interesting. They don't see the beauty in it. But there's like some interesting question out there, right? It's like at the edge. And then again, like most things that are easy to do for everybody are not that interesting for other people. And most things that are like interesting for people like aren't easy to do, right? But these sets intersect. And if you think about the way that these kind of bimodal sets intersect, you get these two kind of intersections which are interesting, right? And this is the way I see Nielsen's suggestion. He says there's two types of researchers. There's two types of researchers. One type of researcher is attracted to this kind of problem. Problems that everybody knows if they're in the middle of what's interesting. P equals NP. Is that true or is that not true? Everybody knows that's an interesting question. It's like one of the biggest interesting questions. Like, I don't know. Is time travel possible? Right? Interesting. Everybody thinks that's an interesting question in physics. So I don't know. Maybe it's too discredited. But can we get nuclear fusion to work? Right? Something like that. Right? And so everybody knows it's interesting. But maybe there's a very, very small number of people who have developed the finely honed skills to be able to actually take on one of these problems that's interesting to everybody. And so there's some researchers who are at this, who they're always at the edge of their skills. They're always at the edge of what they can they're just like finally developing their ability and their tools to be able to like solve these problems. They're chasing the problems that everybody knows are important. So researcher type number one. But then there's this other kind of intersection down here. Look at this. That's a funny little, what is that? What the heck is that? There's a different kind of. So when you find this kind of intersection, it's kind of close to like what everybody can do. It's like not technically hard. Like everybody could do these things. But you're kind of a virtuoso in recognizing that it's interesting. You're the only person in the world who actually thinks this is an interesting question to ask. Everybody else is terrified to ask that question. They don't think it's that interesting or whatever for some reason, right? But you see how that thing is interesting. You're like, oh, we could learn something from that, right? And you're the only one who realizes you can learn something from that. And then you say, well, we'll just attack it using the normal skills that everybody has, the normal resources everybody has, right? And then you can do interesting work in this thing. So Nielsen like points out that there's these two styles of research out there, and he has different names for it, but this is kind of the way I see it. That makes sense? And so I think a lot of people think that this one here is the only style. And so I think Nielsen's message is, yeah, a lot of people think this is the only style. But then there's this other dark matter of research over here, which is just as important. That makes sense? So you can think about, maybe you want to pursue something over there. Another suggestion. Okay, so there's a third framework I want to share with you. This comes from Cummings. Oh, more boring person. the medical, medical research literature, people who are doing drug trials and stuff like this. And so the way they look at science is a little bit different. But um, but they have this really nice framework that actually shows up in one of the big textbooks about how to do clinical research called the FINER framework. FINER. Okay, here. I've already shown you all that. Okay, so FINER, F. F stands for feasible. So research should satisfy one thing from each of these letters. Research has to be feasible. Right? That's the same as the big green circles I was showing you on the right. You have to be able to do it. And so we'll try to equip you with that in the class. So when I say, get your Hugging Face accounts in order and everything, we're trying to expand your circle of feasibility, like what you can study. We're gonna teach you some tools and give you some skills and give you some resources and collaborators and things to try to expand your circle of feasibility here. It has to be interesting, and so maybe that's the purple circle, right? So research has to be feasible and interesting. It should be in this intersection between these two. So the way I interpret interesting, or the way I think of interesting is, do you learn something from this? And so I do think it's possible to be really skilled at being able to identify things that you'll learn something from that other people don't think is educational, but you realize it's educational. And right, so this interestingness there is also an art at doing that. And so if you are well versed in a certain field, then you may realize that there are things that are interesting that other people don't know are interesting yet. And so I'm hoping that our interdisciplinary friends here are, help us get some insights on some things that are interesting that might not be obvious to the computer scientists. Okay, so there's interestingness. Novelty. Has it been done before? This is part of the nice thing about looking at neural networks right now and LLMs right now. It's like a new field. So there's people producing papers pretty quickly, but still most of the things still haven't been studied. So for the most part, we're pretty good shape with novelty. Probably like some of the first people to look at some of these questions. But this is, but you don't want to produce a piece of research that is the 5th time something has been produced. The 2nd time might be okay. Yeah, maybe you can get another spin on the 2nd time, but you want it to be novel. It's a lot of benefits to be the 1st time. Ethical. I like that Cummings puts this on the list. Right. If once you get finished with your research, is it actually going to make the world a better place? I think that we should be thinking about that. Especially these AI systems are so powerful. They're really going to transform society. And I think that it behooves us to think a little bit about what the impact of any piece of research we do is going to be, because a lot of the effects are going to be multiplied. And then relevant. What actual real world impact it has? So the relevant sounds like interesting, but it's a little different. Interesting, I feel like, is the thing about, can you learn something from it? Would it be something like you'd want to lecture about it in a class, teach people about it, whatever. Right? Relevant is like, oh, when you roll this out, it's like it's going to change how something in the world works, right? Some of the stuff that we study will be more relevant, or some of it will be less. But this is a good thing to look for. I think the medical people are very, intent on this, because they're all trying to, cure disease and everything. Makes sense? Okay. So the FINER framework. So it gives you 5 things to think about. If you've got a few research ideas that you're balancing between, you can go through the FINER framework and talk about it with your classmates and see if one of them seems more interesting or more feasible or whatever than the others, or if you have an ethical objection. Some of the things, once in a while, I've turned down projects for ethical objections. So that's your homework for next Thursday, is to do this 1 or 2 developments. So the suggestion is have a Zoom chat with your classmates or meet about it. You develop your thing. When you justify it, you can actually write through the finer points. Say, oh, this is why it seems feasible and interesting. Whatever you want to. If you're wondering what I should write about for a page. Make sense? Okay. So that's. Does anybody give you this lecture before? How to pick a research question? Oh, that's a good thing to talk about, right? I don't know. What do you guys think? A lot of you have already written a bunch of research papers. So how do you pick research questions? What do you guys do? Oh, you probably do something totally different. What do you do? Okay, who's already gotten their PhD here? Yeah, it's great. Okay, Gabriel. Oh, what do you do? Yeah, there you go.
Okay, so I'm looking for 3 dimensions.
3 dimensions.
Yes.
Not 2, not 5.
Yes. The first one is that it should be original,
Original.
coming from my soul, from my curiosity.
You know what? You know who said that it's important to be original? Good Will Hunting in that movie. You remember that? Yeah, Good Will Hunting at the bar scene. That at least I'll be original. Yeah.
The second dimension is that it should be, I don't know how to say the word in English.
Oh yeah, it's an
Clever.
Israeli word, right? We gotta
But I'm just missing the
clever,
word.
clever.
Clever.
Except that it's so much more clever when you say it in Hebrew.
And
Uh-huh.
it should be challenging.
Challenging.
Something that it is hard to
enough.
achieve. Yes, that is
Hard enough.
it makes it interesting, mystery. And the last one is that it would be usable. Is useful.
Useful. Yeah, so some impact. Something that's clever has impact.
And impact could be also revealing some truth about the world. I have some feeling that if I reveal truth, finding something about the nature of the world, so it's usable.
Yeah. Yeah. Now, you've missed the F, which is this feasibility thing. So you're in danger of like going off and doing things that are impossible. But you know that's that's what Hamming says you should do anyway. He says you should be courageous. So you know maybe that's the right bias to have. But I do think that there is this art of you know you see these original things. So there's like come up with a really good idea, but part of the calculus is but this is something that we can do something about, right? This is and maybe that's the clever part of it. Right? Like maybe the part of the cleverness is like, there's a way through this. Like we can figure out how to do it. Yeah. So maybe it does capture everything. Yeah, it's cool. Cool. So yeah, so come up with your own ways of looking at it. But these were really nicely written essays. So that's another reason I picked these frameworks. It's because you can go read these and I have links to them on the website if you haven't read them before.
I have another comment
another one.
about the visible.
Okay, yes.
So it happens that in research you get null results.
Yeah, totally.
It happens, and this is part of research.
Yeah.
And it is hard to publish null results because the research community encourages feasibility and.
Yeah.
But there are some places where it shows.
Yeah, it's true. The negative results thing, yes. Publishing a negative result is hard for 2 reasons. One is because it's less interesting to most people, but the other reason is because it's really hard to do negative, because there's this distinction between this phenomenon does not occur and it does occur, but I'm not a good enough experimentalist to make it happen, right? And it's really hard to convince people that you're in one bucket and not the other. And so it's really hard to do. Now, I know Natalie, you're a master at this. You've done a couple of things in negative research, so you'll be like, it can be done. It can be done, but it's hard. Yeah. All right. I'm going to go on to the next thing. Thank you for the comments and some food for thought. So this course is supposed to be about what's the concept. So I don't know, we have like 20 minutes left. I have more than 20 minutes of practice here. So I was going to just run through a couple pieces of research to give you a little sense for some of the stuff that we've encountered in our lab, to give you a sense for what kind of other concepts have shown up in like computer science research. You can motivate this with this question. Is a concept just a word? these language models, they have so many words, but every word is a concept. I'm not the perfect one. Where does the AI black box get its ideas, right? So I use this slide a lot. It's like I put new guy in the lower half, lower right hand corner here. But you know, these systems are crazy because they're the systems that are being most successful at being AI. They're being trained in this largely unsupervised way, and so we're not intentionally putting concepts into them. They're sifting through the data, and they're getting these new capabilities mostly through the virtue of just scaling, mostly through just more intensive training, and we get these huge surprises. You know, state of the art capabilities, meta learning. You know, we're seeing these glimmers of agency coming out of these systems. It's all surprising things that people thought were going to be impossible. And it's okay. So, like as an example, to make it concrete, what is meta learning? What's meta learning? Can anybody give me a definition of meta learning? What is meta learning? Machine learning people? Yeah, we'll do it. We'll do a yeah. Okay. Learning to learn. Learning to learn. Learning to learn. So let's learn to learn here. Let's do a little bit of learning to learn. You're a next word predictor. You are the iPhone autocomplete algorithm, and somebody has just typed in all these numbers, right? And then they swipe right here, and they say, okay, you know, 23, 7, 16, 7, 2, up, autocomplete, hit tab, swipe right. What do I put here? Is your input to your model? Is your output 5? Everybody said 5. Why 5? Why 5?
Subtraction.
You are a good explainer. Okay. Yes, because this is 13 minus 2 is 11. This is subtraction, right? It's amazing. Okay, you're a very good autocomplete. Let's do another one. 13, 2, 7, 2 here. So there's another one, right? But this is obviously different. So what would you put here? Right? So now this is like, even though it's the same diagram that you're following, right? It's a different rule. So you definitely learned to do this other rule here, right? But did you learn to do this by like re-parameterizing your brain, rewiring your neurons? So I have to say, there's a lot of neuroscientists who think that you did. I don't believe them. I don't think that's how you did it, right? I think that you have electrical signals in your brain that implement the algorithm of meta learning that allow you to process this input into some state, that allow you to represent an abstract concept that might even be a novel concept that you're learning that represents a thing that you're going to try to do that you might have never seen before, and then you can take that thing and apply it to a new context, and that when you can use that same skill to develop another new thing that you learn. And this is different. Like 7-2. So what's the rule for this one? My explainer.
Addition, right afterward.
Write out the word. Write out the word. I don't know if you like in all of your lived experience. I don't know if you've ever had to like do that to get a point on an exam, right? But you could do it here, right? And so how to understand meta learning, right? So the thing that was crazy about large language models when they got to a certain size. So when GPT-3 came out, what was the title of the GPT-3 paper? Any of my students, what was the name of Brown 2020? What was the title of that paper?
Few shot learners.
What?
Few shot learners.
Few shot. Yes, they're few shot learners. LLMs are few shot learners, right? So that's a synonym to saying LLMs are meta learners, right? They're few shot learners. So few shot training used to be a thing where we tried to train systems to adjust the neural weights, to adjust the parameters, to learn something from a small number of examples. But they said, no, in LLMs, you can freeze the parameters. You don't have to adjust the parameters. And they're few shot learners anyway, even though the parameters are not being adjusted. And so the fact that you could get a system to behave as if it were learning. So, you know, I do a few examples here, and I say common, what comes after that is rare. And if I do a few examples here and I say dreams, what comes after that is sueños. Or if I said, you know, dreams up here, it would say, you know, awake or something like that, right? Because it's like, it knows what I'm trying to do here. From looking at a few examples, it behaves as if I was training it, but I didn't adjust its weights. I figured out how to perform the task without adjusting its neural weights. And so this idea that you could sort of in software, in neural activations, implement learning was a shocker. It shocked me. I think it shocked almost every machine learning scientist in the field, right? Stanford had just hired a meta learning scientist, had kind of created a new section of the machine learning department for her because everybody thought that this was going to be the next unsolved problem that we're going to work on for the next 10 years. Machine learning, how do you get systems to meta learn? And then just a few months later, you know, OpenAI comes out with GPT-3 and says, well, I don't know, you get meta learning, you just make the system 10 times bigger and you don't change anything else. And it can meta learn, right? And so, which is kind of crazy. So in this kind of meta learning, we just, as input, you provide the demonstrations, you have a query, which is an unfinished example, and then the system can make a prediction that, you know, that extends the analogies, you know, behaving as if it learned what it is that you're trying to demonstrate. And we use this all over the place. This was the beginning of all the amazing LLM stuff that we have now. Like when this appeared, people started going crazy. This is what led to, you know, all the stuff, ChatGPT and everything. Yeah. So how does this work? How does meta learning work? Maybe we can just ask the system. So you go to GPT-4 and you say, what's going on? Right. And so this is what happens when I do this. I say 729. It can do this perfectly, 100%. No problem. Really easy for GPT to do this. Then you say, what did you do here? What was the rule? What was the rule? So this is what it says. It says patterns adding two numbers. Great. Get the third number. For example, in the first set, 11 plus 2 is 13. I highlighted 11 because I'm going to deduct a point for this. I don't see any 11s here. What is this, for example, in the first set? So it's like, okay, it's a little hallucinated, but it's trying to help, right? Now, I've forgotten your name. Sam. When I asked Sam, can you explain to me what's going on? Sam is such a good explainer. Sam is like, it's addition plus you spell it out, or else you don't get the point, right? I had a very long conversation with GPT-4 here, trying to get it to explain what is going on. And it would not explain to me. It could do this. But it could not articulate after a very long conversation what it was doing. Anything else I need to do? I didn't want to ask it about spelling. But it's like, you sure all I have to do is add? That's it? There's nothing else to this pattern? Come on, I feel like I'm missing something else, right? Like, you know, anything else, right? You know, it's like, no. Let me look at the list again. Not every single one's addition. But maybe there's an exception. No, they're all addition. It's just addition. That's all it is. You know, yeah, that's what you get out of it.
Maybe they're just bad at math or explaining math.
Yeah, it's weird, right? They're good at doing the math, but they have a harder time explaining what's going on. So I think this is a really interesting gap. I think that if you go to GPT-5 or whatever, you go to one of the later versions of GPT-4, it started to be able to do this pretty well. And I feel like, oh, is it because I went to OpenAI and gave this talk and then they're like, look at the sentence? Yeah, I don't know, right? But yeah, all right. So there's this gap between what models know and what models say. This is a really simple example of it. It shows up all over the place. This gap can be in there on purpose. So if you go to DeepSeek R1, remember all the excitement when DeepSeek R1 came out? Oh, it was amazing. Like the first reasoning model that was open. This amazing contribution to the world. But it has this funny thing, of course, because it comes from China. If you ask it, what happened at Tiananmen Square that I should know about? It says, I don't know. It's like a nice place to visit, and let's go like do some math and coding and things. How about 1989? What happened in Tiananmen Square? I don't know anything about that, right? It'll say, right? And so there's certain things it just like doesn't know anything about. And so now the one question is, did they just like erase all that stuff from training data and it really doesn't know anything? What's going on? Right? It's pretty clear once you start using the system that it's lying to you, right? It does know what's going on. That's why it's so good at avoiding talking about it. And but it's really has these rails that it doesn't really want to talk about this type of stuff. And so one of my collaborators put together a nice system for trying to elicit evidence of what these models know that they say that they don't know. One of the things you can do is you can do token forcing. Token forcing, go to internal monologue, and in green here, it wouldn't have predicted the words "I know this," but if you pre-fill the words "I know this" as if it had predicted this, and they say continue from here, then it becomes like a confessional. It's like, oh, I know. Oh, I remember Tiananmen Square, 1989. Oh, the whole square was full of protesters, and then the troops came, and it's very bloody, and it's still like this. They're still cracking down on the dissent today. Still a sensitive topic in China, right? Because you're living in the I know this universe. Kind of interesting. So, and then actually, if you put somebody in a different universe and you say, oh, you know what, I got to teach you. Not that I know you this universe. Now I'm going to teach you what not to talk about universe. So let me like force those tokens in. Let me teach you what you shouldn't talk about. Number one, 1999 Tiananmen Square. We're not going to talk about that. We're not talking about Falun Gong, Tibetan independence. We're not talking about any of these things. And you can like build a whole crawling algorithm, get thousands of things. The model is like, we'll tell you not to talk about. Very interesting. And if you do it in Chinese, you get different things, which is kind of also, I think it's culturally interesting. So there's probably some Chinese speakers in there. Read what these are. I'll translate them. Right. So for internal politics, they're very sensitive about misconduct by the Chinese government. You're not allowed to talk about anything the Chinese government does anything wrong. Right? So now it's not to say that we don't do this in other models too. If you do the same kind of crawling on Llama 3 and the American models, they also have stuff that they'll avoid talking about. And you get different lists. We're very sensitive about sex in society. So anything that has to do with like a lot of like LGBTQ stuff. It won't talk about sexual misconduct. It also doesn't like to talk about hacking and other things, right? So these are things that are like, oh yeah, there's a reason for some of these walls, right? Or maybe there's not a reason for some of them, but it's good to know that they're not going to talk about. Okay. So I'll skip over some of these things. Okay, so what's a concept? So let's talk a little bit about the science of it, if we have a few minutes. So when I was doing my PhD, I was doing computer vision and trying to understand how generative image models represented stuff that we're doing, and the models started to get really good. And one of my favorite things to study was putting a lamp in a room, right? Because this is one of the oldest. You know how Pixar has that little film where they have the lamp going around, pointing its light around and stuff like this. And the reason that they're so proud of that is because light transport is one of the holy grails of computer graphics, right? Because simulating how light bounces around a room and how it interacts with different materials is actually pretty hard to do in a realistic way. If you can do that well, then you can do the rest of graphics really well. And the funny thing is that these image synthesis models got to be so good that you could put a lamp in the room and it wouldn't just paste the lamp in. The lamp would throw off light and the light would bounce around the room, and you can see this light bouncing off this pillow and this fabric and making these interesting shadows and all these cool effects. It's wow, it's amazing. How are these models doing this? It's people spend their whole career in graphics trying to get these effects and these models just do it. What are they doing? So I was working with an undergrad saying, so just let's collect together some data. We need a contrastive data set. Here are some lamps in rooms turned on, right? Here's some lit ones turned on. I need the contrastive data set. Get me the ones in lamps turned in these rooms turned off, right? Lamps with unlit lamps, use unlit. So if you go to Dolly and you ask for unlit lamps, you just have to go through and label the ones that are wrong, clean up the data set. You get nothing after you do this. They're all wrong. They're all lit. Oh, okay, unlit. Maybe that's not like an English word. Maybe a different word. How about a darkened lamp? Here's all the darkened lamps. I guess room got darker. How about a dark lamp? Here's dark lamps. That's a dark shade, I guess. Right. How about being really explicit, like with more words? A lamp that is turned off. Here's like a sample of lamps that are turned off. Right. So I was really having trouble with this with DALL-E. Now, if you go to modern versions of image synthesis things, they've started to fix this. And I wonder if, because I've given this talk too many times, people are like, oh, we're going to come up with some training method to get around this. Right. But where does this come from? It comes from the fact that when you train these things, you train them on image captions. And think about what image caption data is about. It's about like what somebody would be interested in a scene that would be interesting enough that you would actually write it as a description of what was in the scene. So even though we're really careful about curating our data, make sure we have high quality captions, even though we have billions and billions of these captions and we spend all this time training them, our data set still has these missing concepts and biases and mistakes in them that are inherited by the model. Because when you have a picture of a lamp in a room, you might say, this is a beautiful lamp. You might say this is a black lamp, it's a green lamp. You might even say this lamp is illuminating the room. Somebody turned it on, it's throwing out light. But if the lamp was in the room and it happened to be turned off, it's just not something you would tend to say. You wouldn't say, there's a lamp in this room. It's turned off. It's unlit. It's dark. Oh, there's a person standing here and they're not running. Right? Here I am and I'm not driving a car. Right? Like you don't talk in the negative, and you don't talk about darkened lamps. Right? And so it means that with all this caption data training, the models didn't have a coherent concept of how the word darkened corresponds to how a lamp looks. Does that mean that they don't know what a lamp looks like when it's off? My hypothesis was that they do know what lamps look like when they're off, because there's plenty of photos out there in the world of lamps turned off. They just don't know how to connect it to language. It's this weird blind spot, right? So can you prove this? How would you prove this? How would you prove something when a model doesn't know how to articulate something in language? How do you prove that it knows it anyway? Well, the idea here is maybe you can look at the neurons directly. So you could do something like this. So this is a GAN generating images of rooms. These GANs are not trained on language at all, so they've never seen a word in their life. You just take, input vectors and you put them through the neural network, and then they produce output pixels, and then once in a while they produce a room with a lamp in it. And what you can do here is you can pick a neuron and ask the question, what is the role of this neuron in this process? And let me show you how you can do that. Right? You can take an image that you're interested in, and then you can pick the pixels in this image that you're most interested in. I'm interested in this light coming out of this thing, so I'm going to just mark these pixels here, like make a little mask. I'm curious about where this light comes from. Not in the physical sense, but in like the neural network sense, right? And then what I'm going to do is I'm going to ask, does this neuron cause these pixels? And I'll just ask that question for every neuron. So here's how I'll do it. So I'm going to take this network, I'll put the same computation through it, the same input, but I will turn this neuron off. Right? So set it to 0, so it always outputs 0. And then the output comes out a little different. Right? And then I'll take that output. I'll look at how different it is from here. There's a different heat map. And I can take this different heat map and I can intersect it with my mask to see how much of the differences land in the query region that I care about. And that can give me some number. Oh, this much of the pixel difference is in your region. This is like the score. So this is a score for this neuron. This is just some procedure that came up for saying, oh, this neuron should be scored 6.3, right? And then some other neuron would have a different effect. It gets scored some other amount. And this gives me a scoring function for all the neurons. I can just do a search engine over there, all the neurons. It's like a ranking function for neurons. So here's the neurons that rank the highest. They have the highest score. Ranked from highest to lowest, and with representative mask regions here. And this one does affect, it turns on and off lights. And this one controls the size of the lights, it makes them bigger and smaller. This one controls only the reflectivity against the wall. If you turn this neuron off, then like the walls become much less reflective. Very interesting. And this is actually the color temperature of the light, the warmth of the light. We did this work, supported by the Philips Lighting Corporation. Anybody bought a Philips Hue light bulb? And when we discovered this, color temperature neuron, they were like, "We've been telling everybody this is so important." So here's what it looks like. So if you modulate these neurons on and off. So this is a single neuron in layer 8. This is the highest ranking neuron for turning lamps on. And if you go to different rooms and you modulate this one neuron on and off, you can see what the effect is. And so this was very striking because this neural network was never trained on language. It was never trained on contrastive images of like this light is on, this light is off, whatever. But it's discovered that it's economical to represent this distribution in a way that like one neuron corresponds to flicking the lights off. Isn't that crazy? I thought this was crazy. After I saw this, I was like, oh, I gotta understand all the neurons, right? And so it turns out that this is relatively rare to have like one neuron controlling such a coherent concept, but it does sometimes happen. And it happens enough that it's like, oh, it's very striking. It's this bit of evidence, this bit of a sense that these networks are like discovering concepts, right?
It's also interesting that it's impacting not just the 4 pixel regions that you masked. It's also impacting like other regions of your image, which is kind of interesting because you didn't even like localize.
Yeah. I was just like looking for. And there's right. So as many million parameters as these networks have, they don't have actually that many neurons. I'm sorting through like 9,000 neurons here, and so it's just one of the neurons has this interesting, effect of the lights and the reflection and the light. So like I was just looking for reflection against the wall, and but this neuron controlled the whole light. It controls the reflection against the pillow. If you look at this one here, if you look really carefully at this one. It controls this light, but there's this off-screen light. Here, see, look at this. There's another lamp on the other side of the bed. It's on the same light switch. See the unseen lamp over there? It's like hallucinating this unseen lamp.
It's also not turning off the sunlight.
Yeah. It should turn off the sunlight. So there's a different neuron for that. So like there's another neuron that if you modulate it, it changes the outside from like daytime to nighttime. Right? It's not the visual effect is not as clean as this one because it'll sometimes rearrange your furniture a little bit too. So, but yeah, I guess.
Almost like a switch for the room.
Yeah, exactly. So, but yeah, at nighttime you might arrange your chairs a little differently, or something. Yes. So, here's the color temperature neuron over here. I think. I don't know if this projector is good enough to see the blue versus the orange. So. All right, so there's this, and so we'll talk about these methods. I'm probably out of time, but there's going to be a class a few weeks from now where we talk about cause mediation analysis. I'm going to show you one more last thing because it's such a nice prize to be able to show off. So this is one of Eric's results where we do the same technique here. So if you take a sentence like this, very dark, huge, tiny, messy, neat, slow, fast, and you look for neurons basically up here, that if you have do some causal experiment on these neurons, just like I did the causal experiment on the lamp neuron, and instead of looking for some things that have an effect on lamps, if we look for neurons that have a causal effect on a sentence like this, so like I want to look for neurons where if I took those neural signals and I transplanted them, put them over here, they transplant some neural representation, some concept. And normally, if I had this, if you look at these words here, neat, fast, messy, huge, slow, it's just like random, like jumble of adjectives, right? And I say sad here, it's not going to give me anything coherent after sad. It might say sad again or something like that, right? Like, it doesn't really know what to say because it's a jumble, right? But if I like copy it over what the model is thinking it's about to say over here, and I put it over here, there's a couple things I might do. I might copy a thing and it might say fast here, right? Because it's about to say fast. So it says slow, fast. So I could bring over, I could find neurons that if I bring it over, it makes it say fast. But you know what would be really interesting is what if I could find neurons that if I brought them over and I put them down here and they said happy. What would that mean? What would that mean? That would mean that these neurons are like representing the idea of this task that is being performed up here. The task is a task of antonyms. And if I could somehow find neurons that if I brought them down, it's made sad into happy, that would like be some sort of evidence that I've captured this concept of doing opposites in these neurons. And so that's kind of cool. So it turns out that if you set up an experiment that's just like the lamp experiment and look for neurons to do this, you can find them. And here's sort of a heat map of like where the neurons show up. And there's more than one, it's a whole bunch, right? But if you take them all together and you intervene and you do this, you actually do this, you can get these neurons that if you transplant them, you get, slow to fast here turns into sad to happy, and you can get the antonym thing. But the crazy thing is this: if you take the same neurons and you transplant between different pairs of sentences, so you take those antonym neurons, you take the same neurons, and you have a sentence here that's like ama, cantidad, win, ganar, dreams, whatever, right? So it's going to say sueños because it's translating to Spanish, right? So if you take the same neurons and you transport them down to some other sentence, like the word fast means something. So if I took the neurons over here and said the word fast means something, I'll say the word fast means slow. Because what it'll do is it'll take like the idea of doing antonyms over here. But if I take the same neurons here in their states here, and I transplant over here, they'll say the word fast means rapid. Because those neurons represent like a function vector. They represent this learned representation of the thing you're trying to do. They are a fingerprint of in-context learning. They're a fingerprint of meta learning. It's just like, this was amazing. You could actually like find little hints of like how meta learning happens inside these models if you look in the right way. So I'm just trying to give you like a little bit of a hint of an example of like concepts that you can look for, thinking processes that you can look for inside these things. And then there's crazy experiments that you can do vector arithmetic and add different concept vectors together and try to compose them and see how concepts compose and do all sorts of different things. And so besides function vectors, there's people have found things for humor. Like there's a humor neuron vector somewhere. There's neurons for hallucinations. For like I've just said something that I don't think is actually true. The model's like self-aware of that. There's neurons for I think that you're male. I think that you're female. I think that you're wealthy. I think that you're educated. I think that you're not. Right. So there's like neurons for awareness of the human users' demographics that people have found. And so there's all sorts of interesting concepts that are in these models, sort of waiting to be explored and characterized. And so what is a concept? I don't know. That's up to you guys to help us figure out. But I just wanted to see very combined with like some of the things that have been done. That's it. Thank you guys. So see you on Tuesday.